All right, so next up we have Feige Wang telling us about environments and clustering of distant quasars in AGN.
All right, thank you. It's my pleasure to be here to talk about quasars and AGNs using Roman telescope. And actually, I was when I was a student many years ago, and when I see the first name of WFIRST, so this is an amazing telescope that we should use. But now it's really time to get excited about how to using Roman to study those high-resolution quasars. And my talk will be mostly talking about the large-scale environment and the clustering of quasars. Since there are many talks in the morning session and also yesterday talking about the quasars, little red dots, and AGNs, so I will skip all the introductions and go straight to the questions that I wanted to answer. The main question I wanted to answer is whether, how we can grow such massive supermassive black holes in the early universe in the lambda CDM cosmological contact. So if you want to connect a population with a cosmology, you need to know their dark matter halos, right? As you mentioned, the high-resolution quasar density declines really fast, especially deep into the epoch of reionization. The number density is pretty low. For example, at resolution 6.7, the number density is 0.4 per gigaparsec cube. That means you can only find one quasar hosting billion solar mass black holes within 100 square degree. So if you do a naive abundance matching between the quasar number density and the dark matter halos, what you can get is with the assumption of all the massive halos hosting a quasar, what you can get is the quasars needed to be hosted by halos with a mass above 5 times 10 to the 12 solar masses at resolution 7. So this is extremely massive halos. But observationally, how to measure that, it's very difficult. But first, we can look at the simulations. Here, I just saw an example from the cosmological simulation by Tiago Costa. And what he found is when you look at the simulations and try to find the billion solar mass black holes, you have to go to the overdense region or the node of cosmic web where you have a very massive halo and it has a billion solar mass black holes. But if you go to an average region of the universe, you cannot really form a billion solar mass black hole. So the simulation do suggest that luminous quasars in the early universe should be hosted by massive halos and tracing large-scale overdense structures. But observationally, it's really difficult, as we have heard yesterday and this morning about using clustering to measure halos or try to measure halos of little red dots. But for quasars, the number density is so low that you cannot really do the two-point correlation function directly. But there is one alternative way. Instead of doing the autocorrelation function directly, you can try to find more abundant, fainter galaxies around those luminous quasars. If those more abundant, fainter galaxies and the quasars tracing the same underlying dark matter density, and then you can try to measure the quasar-galaxy cross-correlation function. And also you can measure the galaxy autocorrelation function. So based on these two, you can infer the autocorrelation function of quasars and try to infer their dark matter halo mass. That's what we have been trying to do with JWST. Here is a program called Aspire. We tried to use the JWST near-time wide-field slitless spectroscopic survey mode to surveying galaxies around a sample of flux-limited sample of quasars at redshift 6.5 to 7. One of the major reasons we choose this redshift is we put the oxygen 3 emission lines, the brightest emission line. One of the brightest emission lines in early galaxies falls into the sweet spot of JWST, so it can maximize your survey limit. And also at the same time, these quasars at the cosmic organization, you can start many other things as well. This quasar mostly focusing on the radio quiet quasars. There is another program, Cycle 5 program that we will get data soon. It's about radio loud quasars. It adds slightly lower redshift, but we wanted to figure out whether the radio jets plays a different role in the connection between quasars and the dark matter halos. Stay tuned on that program. So in this talk, I will mostly focusing on the radio quiet version of the Aspire. All right, so here I show the emission line galaxies that we found from the slitless spectroscopic survey. From the Aspire observations of 25 quasar fields, we found about 500 galaxies at redshift between 5.3 and 7. So the slitless spectroscopic survey is really powerful, allows you to pick up those galaxies directly without doing any pre-selection. That's why I really like the slitless spectroscopy, and Roman will also provide that, but with a much larger area. So based on the redshift distribution of those galaxies, you can see from the right panel, and like there is a peak on the redshift at redshift between 6.5 and redshift 7. This is exactly the redshift range of our targeted quasar. So from this plot, you can simply see that we see galaxy overdensities around the quasars, right? But now with the large number of galaxies we have already found, we can measure the quasar galaxy cross-correlation function as shown in the orange data points. And also, I also draw the red points here, which based on the other ALMA observations, like we're doing ALMA mosaic observation, try to find dusty galaxies, and also do the same thing for the quasar galaxy cross-correlation. And the interesting thing we found is from both quasar and dusty galaxy and quasar oxygen-3 emitter galaxies, we found the strong clustering of those galaxies around the quasars. And from this measurement, we can infer the quasar galaxy autocorrelation length of about 8.7 megaparsec per moving megaparsec, and the halo mass is about 10 times 10 to the 12.3 solar masses. This is really the most massive halos at redshift 7, like corresponding to 4 sigma or 4.5 sigma peak of the initial mass density. So that's the average of the statistical results. But if you look at the individual quasar fields, it has a very different story. And here I show the number of companion galaxies, or the galaxies at the quasar redshift among 25 Aspire quasar fields. And the black dashed line here is basically the expected number of galaxies among random field, so when you do not have a quasar. So if you have more than one galaxy, it means a quasar residing in overdensity. If you have less than one, then there is no overdensity. What they found is 18 of them residing in galaxy overdensities. And in particular, there are 7 of them with extreme galaxy overdensity, with overdensity above 5 or so. And this is like over volume of several hundred co-moving megaparsec. Means like it's huge galaxy overdensity, and they could be the progenitor of galaxy clusters we see today. But since the JWST field view is too small, we cannot really see the fate of this structure. We cannot really tell whether they will evolve into galaxy cluster or not. But we did some follow-up observations. In the left panel shows some 6-pointing JWST mosaic observations, and we found the structure is still extending like close to the edge of our mosaic. And then we also did some ground-based observation for quasars at a specific redshift 6.6, where you do not have strong sky emission lines, so you can go extremely deep and to 13 lemma meters around those quasars. And this field view is 1.5 degree diameter from the Subaru HSC. You can see how big of the structure is. And this is definitely a progenitor of galaxy clusters. So again, because of the limited field view of JWST, we really needed Roman to starting such kind of large structures in the early universe. This is all about quasars. How about the AGN? I only wanted to talk about this very briefly, as people have discussed many things about the little red dots. And one thing we noticed in Aspire is from one of the little red dots, we found several companion galaxies around these little red dots, meaning that they may reside in similar environment as quasars, chasing galaxy overdensities. But then we have a new program called Cosmos 3D, which is a Cycle 3 LAS program. And from this program, we found about 100 little red dots spectroscopically confirmed. And now we can also do the clustering measurement for those little red dots, as shown in the red dots here. And the black dots in this plot is the clustering of random H-alpha emitters. So they do not have a compact morphology. They do not have a bar line, so just the H-alpha emitter galaxies with a typical halo mass of 10 to the 11 or so. And from our clustering measurement of both little red dots and H-alpha emitters, we see that the clustering strength of little red dots is similar to that of 8.5-meter galaxies, which means that the halo mass of the little red dots is about at least 1 order of magnitude lower than what you got from quasars, so they are quite different halo masses. So from this JWST observations, it tells us 3 things. One, quasars inhibit massive halos, but the environment is quite diverse, right? And the second, the structures, the overdense structure traced by the quasars, and could extend well beyond 10 cubic per sec. And the third, the JWST discovered little red dots reside in different halos from quasars. So we learned so much things from JWST, but it also raised new questions. Like, what's the physical reasons behind this diverse environment? We needed to figure that out. And whether they are caused by different quasar triggering mechanism, or they are like living initially different halos, or have different seeding mechanisms. And what's the role of AGN feedback? Like whether it can affect the formation of small galaxies that cause that you do not see the overdensity, or because of other reasons. And how large of the structures traced by those quasars, and are they progenitors of galaxy clusters, and whether little red dots are the progenitors of quasars. So we needed to figure this out, and Roman will do that. Specifically, there are 3 programs that we really wanted to do. One is to identify O3 emitters around those redshift 2 to 3 quasars, and also faint AGNs and little red dots. We wanted to do a comprehensive study of the quasar, AGN, little red dots, cross-correlation with O3 emitters, and also for some cases, we can also do the autocorrelation function to try to figure out the halo mass of those different populations and make it in the different physical parameter beams and try to figure out which physical parameters drive the different clustering signal. And also, we wanted to searching for the LBGs around high-redshift quasars and AGNs, try to combining LSSC and the Roman. And thirdly, we wanted to using new algorithm observations to search for LAEs around high-redshift quasars and to do the clustering at high redshift and also constrain the cosmic organization. I just quickly show you why we want to use LBGs for, like you already have O3 emitter, why you wanted to do LBGs. One thing is about the role of AGN feedback. Those oxygen 3 emitters really tracing small galaxies. And we found that in some, like even at redshift 7, there are many bright galaxies without any emission lines. So we still missing galaxy populations. And we wanted to understand whether those quasars that do not have overdensity is caused by the lack of galaxies, or it's because our tracer we needed to use a different tracer. All right. I will skip the new observation because you may be one of the future panelists to avoid the dear anonymous. But here I leave my summary here, and happy to take any questions.
Thank you. Questions for Feige?
Could you go back to the slide way back that has the beautiful correlation, cross-correlation between the quasar and the galaxies? That was it there. So my first question is, it looks like maybe the data in the inner 3 arc seconds goes up a little bit, and the model predicts that. So first question is, do you think that that may actually be real? And if it is real, and the model predicts that, does that have something to do with the correlation you get from, it's called when you have 2 galaxies in a halo, the so-called 2-halo term, and then of course that doubles the correlation, the quasar, because there's 2 galaxies there? Is that what
yes, that's a really nice question, and thanks for catching that. Yes, this is exactly like what we wanted to figure out. It could be because of the 2-halo term, and there is an enhancement. Actually, if you look at the blue dashed line, that's a prediction from Trinity. Trinity is an empirical model that includes the 2-halo terms, and it predicts like an enhancement at the small scale. And but the purple line, it's only dark matter. It's dark matter only, right? Consistent with dark matter only, there's only 1 halo term, and we think it's the access is a small scale access because of 2-halo term, but we still needed to figure that out because we only have very limited number of galaxies over there. And we also using 2 different tracers. The innermost is from the C+, the dusty galaxies in ALMA, not from JWST. So that's a good question. We want to figure that out, but I think it's to halo term access.
Great. Lee?
When you're talking about the role of feedback, how are you measuring that? Are you just measuring them in terms of the number of nearby sources around it?
So yeah, so like there are some theories to predict that the AGN feedback could suppress the formation of small halos or small galaxies, but not big galaxies. Right? From the Aspire, we found that like some quasars do not reside in overdensity. There are two possibilities. One is it's not in massive halo. Two, it's in massive halo, but the small galaxies are suppressed. Right? That's why we wanted to using LBGs as well and other galaxies. We try to figure out if we do not see the overdensity of O3 emitters, whether because we are missing other galaxy populations. Like if we see they reside in massive halos and surrounding by overdensity of LBGs, but not O3 emitters, that's direct evidence that it's suppressing the formation of O3 emitters. Right.
All right. Well, then let's thank Feige again.